I'm Michael Jura at the UCLA Physics and Astronomy Department. We study right now polluted white dwarfs. These are stars where an asteroid or comet has crashed into the star, and we see the residual of that accretion. We don't image the comet or the asteroid directly. We only see the indirect proof of its existence by the fact that it's found in the spectrum of the white dwarf star. We basically do modeling of the stellar atmospheres and also a little bit of how to explain the emission from the circumstellar disk that is orbiting the white dwarf stars. So we basically have used two tools: the Spitzer Space Telescope to measure the infrared excess associated with the dust that's in the disk orbiting the star, and the Keck telescope at Hawaii to measure optical spectra of the white dwarf. We also have some space telescope data for the ultraviolet spectra of the white dwarfs. So the idea is to combine it all into an integrated picture for the whole object. So what we see is that an ancient asteroid, which has been orbiting the star for however long the star has existed, has its orbit perturbed, and then it is accreted onto the star. Typically it's a two-phase process. First it forms a ring like Saturn's ring, and then that matter is accreted onto the star. It's almost certainly mainly asteroidal material, and we know that because the composition is quite similar to asteroids and meteorites in our own solar system. For example, there's very little water ice in most of them and very little carbon. Volatile elements are quite depleted. It's quite remarkable. Our own Earth, for example, is largely made of four elements: oxygen, silicon, magnesium, and iron. And we're finding that's quite similar, as well as we can tell, in a very small sample, to what we see in extrasolar rocky objects as well. The advantage of the white dwarf studies is that it's probably the most powerful tool we have at the moment for studying bulk composition of extrasolar asteroids and planetesimals.